Welcome back. This is the second video of section 4.2 on the weak topology on a norm space that we started in the previous video. So in this video, we are going to take a closer look at some properties of this strange topology. So we know that the weak topology is contained in the norm topology or the strong topology. But we didn't prove that the inclusion is strict. So could we have equality? This is the question. And the answer is yes. This happens if E is finite dimensional. So if E is a finite dimensional norm space, then the weak topology and the norm topology coincide. Okay, how do we prove that? We just have to prove one inclusion because the weak topology is contained in the norm topology, so we just have to prove the reverse inclusion. So we have to prove that every open set for the norm topology is open for the weak topology. Okay, or that every strongly open set is a weakly open set. Okay, now, so we take a norm open set U, and we consider an arbitrary element x0 in U. Okay, so what is the strategy? How do I prove that U is weakly open? It's enough to prove that U is a neighborhood of all its points in the weak topology. Okay, so we have to find a weak neighborhood of x0, and we know by the previous proposition that any weak neighborhood contains a set of this special form v of x0 f1 fk epsilon. Okay, so we have to find k elements in the dual of E and a positive number epsilon such that this is true. So this is what we'll find these parameters here. So if we prove this, then U will be a weak neighborhood of x0, and therefore U will be open for the weak topology. Okay. Now, since U is open in the norm topology, then by definition there exists a ball of center x0 contained in U. So the ball is the set of x whose distance to x0 is less than r. Okay, so there is no ball in the weak topology. Okay. The role of a ball is played by these sets of these four. So these are the analogs of balls. Okay, so since E is finite dimensional, then it possesses a basis. So if the dimension of E is k, then there is a basis of containing k elements, linearly independent k elements. And by dividing by their norms, we can always assume that the norm of each of these elements is 1. Okay. None of them is 0. Okay, now every x in E, as you know from linear algebra, can be written in a unique way as a linear combination of EI. So here I have some analogy between the concept of a basis of a vector space and the basis of a topology. The idea is the same, that in both cases the basis elements are used to build the space. They are building blocks of the space. So therefore the map that to each x associates its ith coordinate is a map actually, and it's linear. So I call it Fi. Okay, so Fi is just the projection onto EI, if you like. So it's linear, as you may easily check, and it's automatically continuous because E is finite dimensional. So this will be exactly the F1 Fk in this. Okay, and the epsilon will be just r, the radius of this ball, over the dimension of E over K. Okay, so I'm going to prove that this weak neighborhood is contained in the ball, and therefore it's contained in U. Okay. How do I prove that? I take an element in this set, what does it mean? It means that Fi of x minus x0 is between minus epsilon and epsilon, for I from 1 to k. Okay. And then I want to prove that x is in this ball, which means that the norm of x minus x0 is less than r. Okay, so we can write x minus x0 as this linear combination in this form, Fi of x minus x0 ei. And then when you take the norm and use the triangle inequality, the norm of the sum is less than or equal than the sum of the norms, and by homogeneity of the norm, we have, this is a real number once again, okay? So this is a scalar, so it's the absolute value of this scalar times the norm of EI, which is 1. And since x belongs to this weak neighborhood, we said that f of I of x minus x0 in absolute value is less than epsilon. So all the terms are less than epsilon. I have k terms, so the summation will be strictly less than k epsilon, which is r. And therefore, x belongs to the ball of center x0 and reduce r. Therefore, x is a nu, so v is contained in u. And therefore, u is a weak neighborhood of all its points, and therefore u is weakly open. Yeah. So this case is not interesting for us because we didn't do anything new. Okay. Now, let us look what happens in the more interesting case of infinite dimensions. Okay. So let us start with a lemma. If E is an infinite dimensional vector space, not necessarily normed, so, and we have k linear functionals on E, so just linear forms, then the intersection of their kernels is not trivial, which means that it's a proper subspace. It's not reduced to 0, because as you know, a subspace could be reduced to 0. Okay, so I have to prove that there is a non-zero element in this intersection, and this is easy. Maybe you encountered this in a course on algebra. If not, then what does it mean? If I define the map phi from E to Rk, whose components are exactly f1, fk, then the condition that this is 0, what does it mean? It means that if x belongs to the intersection of the kernels, then x is necessarily 0, which is equivalent to saying that if all components are 0, then x is 0. So, and therefore the kernel of phi is 0. So phi would be a linear injection. But as you know from linear algebra, then the dimension of phi of E will be less or equal than the dimension of the target space, so less or equal than k. But so it would be finite dimensional, and this is the contradiction. Therefore, there is a non-zero element in this subspace. Actually, we can prove more. The space is not only not trivial, so it's at least one dimensional. It contains a line, if you like. It's a huge space because it has codimension at most k. So, in particular, it's infinite dimensional. Okay, and I proved this. The proof is a little bit technical. You can read it. It's in the lecture notes. I'm not going to prove it here, but you know that it will be enough for us to use the fact that it's not trivial. So it's at least one dimensional. Okay, so it contains a line through the origin. Okay, now so therefore, next result, if E is an infinite dimensional normed space this time, then a non-empty weakly open subset of E contains a non-trivial affine subspace and is therefore unbounded. Okay, so this is something really specific to infinite dimensional spaces. The weakly open subsets of E that are not, of course, empty are big actually, because they contain a non-trivial affine subspace. So in particular, it's unbounded. Okay. Okay, let us. The proof is very easy actually. It's just a consequence of the previous lemma. So consider a weakly open set, which is not empty, of course. So and consider an element x0 in U. Then U contains, as we know from a previous position, this fundamental set of this form: V x0 f1 fk epsilon. And now, as we observed earlier, x0, why x0 belongs to this? Because when x equal x0, we have fi of 0 is 0. So of course this is a neighborhood of x0. But the most important thing is that even if x is not x0, if x minus x0 belongs to the kernel of fi for every I, then this is 0. So this observation can be written in this way: x0 plus this subspace, intersection of all kernels, is contained in, because if an element is here, then x can be written as x0 plus an element in this kernel. So the difference belongs to the kernels, and therefore this term is 0, and therefore it's less than epsilon, so x is in V. Okay, so this is why V contains a translate of a subspace, an affine subspace, if you like. Okay, so, and therefore, and as you know, a subspace is unbounded, so a weakly open set is unbounded in infinite dimensions. Therefore, in an infinite dimension norm space, the weak topology is strictly smaller than the norm topology, and in this case, it's really something new. And this is the real interest of the weak topology. Why? Because, for example, if you take the open ball, norm open ball, it's strongly open, but it's not weakly open because it's bounded. Okay? Cannot contain a subspace. Therefore, we have found an element in the norm topology which is not in the weak topology. Therefore, we have a strict inclusion. Okay, and I will end this video with a surprising result. As you know, the sphere, the unit sphere in a norm space, is a closed set. It's closed with respect to the norm topology, but it's not closed with respect to the weak topology. And its closure, the weak topology, is the whole ball. Okay, so we say that the weak closure of the unit sphere is the closed unit ball. Okay, or in symbols, SE, S sub E bar weak is just B. Okay. How do I prove that? Double inclusion. Okay, so let us prove first that the closed unit ball is contained in the weak closure of this. How do I prove that an element is in the closure of a set? There is a characterization that you know from second year. A point belongs to the closure of a set if every neighborhood of that point meets the set. Okay, but here we are working in the weak topology, so we have to prove that every weak neighborhood. So we take an element x0 in BE, and you have to prove that every weak neighborhood of x0 meets the sphere. This is the strategy. So consider, take V to be a weak neighborhood of x0, and therefore it contains a special neighborhood of the form Vx0 of 1 f k epsilon. So we can assume that V is of this form, and where epsilon is positive. So if you consider these k linear maps, as we know, since the space is infinite dimensional, the intersection of their kernels is not trivial. So we can find a non-zero element. This is enough. Actually, it's a big space, but I just need to take one non-zero element in it, y0. So there is a non-zero element such that fi of y0 is 0 for every I. And now we consider the function from 0 infinity to r defined by the norm of x0 plus ty0. Okay, so of course this is a continuous map, because combination of linear maps. And moreover, when t equals 0, we get the norm of x0, and x0 was in the ball, so its norm is less or equal than 1. And what happens as t tends to infinity? If we use the second form of the triangle inequality, we can write this as t norm of y0 minus norm of x0. Since norm of y0 is different from 0, then this tends to infinity. So g of t tends to infinity as t tends to infinity, okay, by the second form of the triangle inequality. And since g is continuous, we can use then, so it goes from something less or equal than 1 to something infinite. So of course, it will be bigger than 1. And therefore, at some point, it will be exactly equal to 1. Okay, if it happens that x0 equal to 1 in norm, there's nothing to prove. But in general, if x0 is strictly in norm is strictly less than 1, and since it takes a value bigger than 1 for another value of t, then it must take the value 1 at some point. Okay, and what does it mean that g of t0 equal 1, it means that the norm of x0 plus ty0 is equal to 1, and therefore this guy x0 plus t0 y0 belongs to SE. And now it's easy to check that x0 plus t0 y0 belongs to this neighborhood. Why? Because when I apply fi, fi of x0, so fi of this minus x0 is just fi of t0 y0, but since y0 is on the kernel, then fi of t0 y0 is just t0 fi of y0, which is 0. So this guy actually belongs to the neighborhood, and therefore it belongs to the intersection, and therefore the intersection is not empty, and therefore x0 belongs to the closure in the weak, relative to the weak topology. Okay, the converse. A corollary of the Hahn-Banach theorem, analytic form, can be written in this way. We can write the closed unit ball as the intersection of the inverse image under F of the closed interval minus 1, 1, as F belongs to varies in the closed unit ball of E star. Okay. Now this looks strange, but this is just actually saying that the norm of X is the supremum of F of X. F between for F in the if you write this, so this is equivalent to the corollary, okay, giving the norm of X in terms of the supremum of F of X, F in the closed unit. So just take a paper and a pen and check that. And now it's easy because now since F is continuous in the weak topology, this is a weakly closed set, so the intersection of weakly closed set is closed set. So BE is not only strongly closed, it's also weakly closed. And this is a particular case of a more general theorem that we shall prove in the exercise. Okay, this is due to the convexity of BE. Okay, so therefore BE is weakly closed, and since and so it's a weakly closed set containing SE, but the closure of SE in the weak topology is the smallest closed set, weakly closed set containing SE. Therefore, it's contained in this set. So the closure of SE in the weak topology is contained in BE, and therefore we have double inequality and therefore equality. So in particular, the unit sphere, although it is strongly closed, it's not weakly closed. So we have found a strongly open set which is not weakly, a strongly closed set which is not weakly closed. Therefore, this is another proof that the norm topology and the weak topology are not the same. Okay, so if you are tired, you can pause the video, but I will just, so the last result of this video will be that in an infinite dimension norm space, the weak topology is not metrizable. And this is not difficult. We reason by contradiction. If the weak topology was generated by a distance rho, we'll get a contradiction. So for this, we consider the sequence of these balls, of weakly open balls. They don't exist, but we don't know that yet. So because I'm assuming that, so this is why I denoted by B sub rho, okay, not B0, not the usual ball. Okay, this is the ball with respect to this imaginary distance of center 0 and radius 1 over n. So it's by definition the set of X in the space whose distance with respect to X is less than 1 over n. And once again, this is not the norm of X. Okay. So as you know from the first course in topology, an open ball is an open set. So an open ball belongs to the topology. So in particular, this imaginary ball with respect to rho is a weakly open set. But we know that it should be unbounded because it contains an affine subspace. What does it mean that it's unbounded? It means if you write the negation of the boundedness condition, so bounded means that it's contained in a ball for the norm, okay? So it means that there exists a positive M such that B rho is contained. So if X is in this ball, then the norm of X will be less or equal than M. So if you negate this, you will get this condition. This is unbound for every N. So for every N and for every constant M, I can find an element in this imaginary ball whose norm is bigger than M. This is the negation of the boundedness condition. Because saying that a subset of a norm space is bounded means that it is contained in some ball for the norm and can take the ball to be of center 0. Okay, now closed or open doesn't matter. So this is just the negation of the condition that this ball is bound. Okay, now therefore if I take capital M, and so I vary n, I take n equal m equal 1, then n equal m equal 2, then n equal m equal 3. At each time I get an element that depends on the previous parameter. So it's xn depends on n in this imaginary ball whose norm is bigger or equal than m. Okay, so we have a sequence xn in this imaginary ball. So if each xn is in the ball of, so the ball is shrinking actually. So xn is in this. Okay, what does it mean? It means that the distance with, so rho of 0 and xn is less than 1 over n. And this means that xn converges to 0 with respect to the distance rho, so with respect to the weak topology. But on the other hand, xn is unbound. Okay, and now we get a contradiction because this inequality tells me that xn converges weakly to 0 and therefore it's bounded. But the condition, this inequality tells me that it's unbound. So therefore, my assumption was wrong. There's no such distance. Okay. So therefore, in infinite dimensions, the weak topology is not metrizable, although it's Hausdorff. So this is a natural example of a Hausdorff topology which is not metrizable. Okay, so final remark, although the whole space with the weak topology is not metrizable, but if we restrict the weak topology to a bounded subset of E, then it's possible sometimes, and this is what we shall deal with later, it's possible sometimes that a bounded subset of E with the weak topology, equipped with the weak topology, is metrizable. Okay, so don't confuse these two. This seems contradictory, but the argument that we use about unboundedness, if I take a bounded subset of E, I cannot use this argument anymore. Okay, so the whole space in the weak topology is not metrizable, but a bounded subset of E in the weak topology may be metrizable, and this happens if and only if the dual of E is separable. And this is something that we shall learn in section 4.5. So I will stop here, and in the next video I'm going to talk about convexity and the weak topology. So thank you for your attention and see you next time.